7.3 is estimating P in the binomial distribution. All right, so estimating P, and if you recall, P is the probability of success. Binomial means that there are two outcomes, and we defined those outcomes as success or failure. And if you remember, this was P and this was Q. Probability of success was P, the probability of failure was Q. And P and Q were complements, meaning they had to add up to 1 or 100%. Now, one other thing that I want you to remember is we've been talking about point estimates. So P is your population parameter for a proportion. So this is a population value. Its point estimate is P hat. So this would be calculated on a population. This would be calculated on a sample. This is what we do not know we're going to estimate, so this is its point estimate or its best guess. Recall, a binomial experiment is determined by the number of trials in and the probability of success on a single trial. For most experiments, the number of trials is chosen in advance. Then the distribution is completely determined by P. In this section, we will consider the problem of estimating P, population parameter we do not know, so we will be estimating it, under the assumption that N has already been selected. So here are some assumptions that we are going to make. N has already been selected. The normal curve, meaning the bell curve, is a good approximation, large sample methods. We will use sample estimates for the standard deviation when necessary. So this is just saying if sigma is unknown, you can use S, sample standard deviation. Something that is new here is to justify that the number of trials N is large enough to assume normal approximation, then this criteria must be met. N times P hat has to be greater than 5, and N times Q hat has to be greater than 5. Okay, so point estimates. So point estimates for P and Q are going to be P hat and Q hat. In order to calculate P hat, you use this formula here, which is R, your number of successes, divided by N, your number of trials. And then once you calculate P hat, you can find Q hat because they are complements. Once we have P hat and Q hat, then we can calculate the margin of error. And notice in the margin of error that it says Z sub C. So we're going to go back to using this small table right here. Z sub C times the square root of P hat times Q hat divided by N. And then our confidence interval is P hat minus E and P hat plus E, but notice we're estimating P. So this is now P instead of mu. So let's look at a couple of examples. This first example, it just gives us numbers. They don't tell us what the numbers represent, but we can do the calculations. So we are given that N is equal to 150 trials and R is equal to 60 successes. So the first question asked is it appropriate to use a normal distribution to approximate the P hat distribution? Well, what that is saying is we have to be able to justify that N is large enough to assume normal approximation. So we're going to have to show that this is true. So the first thing that we need is P hat. And P hat is R over N, 60 divided by 150, which is 0.4. And then Q hat is its complement, which would be 0.6. So to show if it is appropriate or not, now what I will do is I will take N, 150, times P hat, 0.4, and I need to find out if that is greater than 5, and N times Q hat must be greater than 5 as well. Well, 150 times 4 is 60, and 60 is definitely greater than 5. And 150 times 0.6 is 90, and 90 is greater than 5. So is it appropriate? Yes, it is, because we've shown that these are both greater than 5. Find a 95% confidence interval for the population proportion of success P. Well, before I can find the confidence interval, I have to find the margin of error. And we know we're going to use Z sub C. Whoops, I'm not going to put it. C is 95%. So Z sub C, 95%, it will be 1.96. So C is 95%, so Z sub C is 1.96. So now we can create or calculate the margin of error. Okay, so the margin of error means we are going to use this formula right here. And that tells me to take Z sub C, 1.96, times the square root of P hat, which we calculated to be 0.4, times Q hat, which we calculated to be 0.6, divided by N, which is 150. So when I put this in my calculator, 1.96 times the square root of 0.4 times 0.6 divided by 150, come out from under the radical, 0.0784. Now, I'm okay if you round that to 0.08, but you'll just have to be careful on WebAssign because you don't want to do too much rounding or it will calculate it incorrectly. So then we get our confidence interval, which is, so we come back here, here's my confidence interval right here, so I need P hat. So P hat is 0.4 minus my margin of error, and we're estimating P, and then P hat plus my margin of error. So we get the confidence interval of 0.3216 and 0.4784. So here's my confidence interval. So if we were asked to explain the confidence interval, which is a little hard because we don't know what these numbers represent, but you could say, I am 95% confident the population proportion is 0.3216 to 0.4784. So that would be an example of an explain. All right, so now a problem that actually refers to something specific. So we have a random sample of 188 books that were purchased at a local bookstore and showed that 66 of those books were murder mysteries. Let P represent the proportion of books sold by this store that are murder mysteries. So they're trying to figure out what percentage or what proportion of books they sell that are actually murder mysteries. So they tell me we have a random sample of 188 books. So N equals 188. So that's your number of trials. And then 66 of these books were murder mysteries. Well, we're defining success as murder mysteries, so the number of successes, or R, is your 66. So it says, what is the point estimate for P? So the point estimate is P hat, which is R, over N. And if you take 66 divided by 188, you get 0.35106. I'm just going to go out 2 decimal places, so approximately 0.35. Be careful with that on WebAssign. Now it asks for the point estimate of P, but I know I'm going to be calculating the margin of error, so I'm going to go ahead and calculate Q hat as well, which they are complements, so that would be 0.65. Now it wants to know what is the margin of error. Well, in order to find the margin of error, I need to know how confident that I am. So in this particular problem, I have to look down here and it says to be 90% confident. So C, whoops, I want Z sub C. So 90%, 1.645. So my margin of error will be 1.645 times the square root of P hat, 0.35, times Q hat, 0.65, divided by N, and N is 188. When you put that into your calculator, you get approximately 0.06. We'll do that real quick. 1.645 times the square root of 0.35 times 0.65 divided by 188. Come out from under the radical. So 0.0572. So on WebAssign, you might want to go out to 0.0572 and so forth. I'm okay with 2 decimal places. Sometimes WebAssign's a little bit pickier. So now my confidence interval, well, my confidence interval is P hat, 0.35, minus my margin of error, and P hat plus my margin of error. So we get 0.29 and 0.41. So based upon my confidence interval, I'm saying that I would guess that they sell 35% of the books they sell are murder mysteries, but it's going to typically be anywhere from 29% to 41%. So I am 90% confident the proportion of murder mysteries sold is 29% to 41%. Something to that effect. And then lastly, it says, is the normal approximation justified? Well, again, that says show that N times P hat is greater than 5 and N times Q hat is greater than 5. So we would take 188 times 0.35 and we would take 188 times 0.65 and you get 65.8, which is definitely greater than 5, and here you get 122.2, which is definitely greater than 5. So yes. And that is how you estimate P.